Everybody can hear me? All right. So today we are going to start with electromagnetic force, then introduce the electrostatic force from that, and then the electrostatic field. And in the process, also we are going to start talking about the need to use vectors and so forth, and why vector properties are important. And I don't believe we'll have time, because I did not have time in the morning to go into vector operators, but we'll do that on Wednesday. I may just try to introduce it depending. Sometimes the first time I give the lecture, it takes me longer. The second time I give the lecture, it takes me shorter. Maybe my brain already eliminates all of the things that were not productive. Okay, so we said on Friday, I believe, that the electromagnetic force expresses itself in 3 different ways. And we mentioned that while it's the same phenomenon that we see in 3 different ways, historically we thought that they were 3 different phenomena, but they are not. They're the same. So an electromagnetic force is a force that is due to a charge. Now this charge can be static, so it has the same value and it is in the same point in space and stays there. And then in that case, the force is called an electrostatic force. Then it can be a charge that is moving with a constant velocity, and then it's called a magnetostatic force. Or it is a charge that is moving with a velocity that changes over time. All right, and then which means that the velocity will accelerate, decelerate, whatever needs to be done for that particular problem or phenomenon. And then in that case, what we see is an electromagnetic force. And what is the difference between these 3? It is the same force expressed in 3 different ways, okay? So what does it really mean? It means that in the most general case, where the charge is moving in an arbitrary way, then the force has 2 components. One is called the electric force, the other is called the magnetic force, and together we make the force. So it's like a force that it has 2 parts, all right? When the same charge now, we force it to go with the same speed, velocity, then one of these terms goes to 0, and it's only the magnetic part of the force that remains, and then we call it magnetostatic. When now this charge, we also stop it, we make it freeze in space and in time, so it becomes constant static, then it's the magnetic part goes away, and it's the electric part of the force that comes up. All right, so it is one force, 3 different ways we see it. Now, why, however, do we look at them instead of looking at the whole thing together? Usually we do that in graduate school, all right? So when you start talking about most general cases, then you look at the full thing. But when we start thinking about electromagnetics in general, we introduce statics first, because there are a lot of things we can get from statics in a simple way that can help us in a whole list of applications today. So everything that we are gonna learn from statics, you can apply to digital circuit design. Yes. All right, thank you for telling me. I don't know why it's not there, but we'll find out. Oh, no, wait. Device, all displays. Okay, 1, 2, Okay. Let me call somebody while, and I will continue until somebody comes, because I don't know exactly what it is. I do exactly what I'm supposed to. Hi, I'm calling from 341. Could you please come upstairs and help me with some of the displays? Thank you. Okay. So we'll resolve that. Okay, so I said we can, if we look at them separately, we can, what? Yes. They are already. It's blocked? Locked. Locked? Okay. So, all right, let me see here. Canvas. This one. Modules. Week 2. They're not blocked. Why are they blocked? Okay. Then let me see something else. It is possible. There are so many places that we need to look at. All of these are checked. All right, so all of these are checked. Go to modules. The module is checked. 2 checked. Is there anything? Where else could it be? Where? No, the red dial is only for pictures in there. Yeah, we need to move it into those.
Okay. So it should just be table displays and then this is here.
Oh, there. Okay.
Oh.
Yeah, we're good. Okay. So for some reason it did. Okay, so that's where we go tables and sources.
Yes, correct.
My device.
Yeah, your device.
Yeah, okay. I thought I heard that, but you know, just so I'll look at the. Let me see. One student. Yes, we'll fix it.
Oh, okay. Okay.
Thank you. Let me do the student view. Student view. What happened? Module 2. Okay. Was not locked?
Yesterday I was able to see everything.
I know. Why would I lock it? So let me go to the folder. So files. Okay, it could be here. There. Yeah, see, that's what the problem is. Okay, got it. So let me go back out of the student view. I got it. Let me see. Student view. Leave student view. Okay. So modules, files.
Yeah, let's see. Hey, $8 a cup or
Um, maybe done. Here. Oh, thank you. Updated. Yeah. Okay. Thank you. That should be there. Thank you. Okay. So okay. So now you have access to it. All right. Let's go there. All right. So why now we do them separately? Because we can get simple formulas that we can easily apply to very difficult problems. All right. And a lot of work has been done on that. So it makes sense for us to use it separately. And as a matter of fact, when the phenomena that you deal with are not complicated, why should you complicate them even more? If, for example, your problem tells you that you only have an electrostatic field, why are you going to bring the magnetostatic? Why are you going to look for electric and magnetic fields if the magnetic fields are not important or don't exist, all right? So that's why we do it this way, but in reality, it's the same thing. Okay, so now having said that, we are going to introduce the electrostatic field. So we start with force. And how do we normally do that? I will start writing things if you have any particular questions, all right? So that's why I am doing this on Notability, because I can add pages and I can write. Okay, so as you know, you have seen from physics, if you have a positive charge here, all right, and then Q1, and then you bring in the vicinity of it a negative charge here, then the two charges will feel an attractive force. Now, this force will always exist, even if it's so weak that we cannot measure it, all right? But it exists. It's not like that it only applies over a particular range. It applies from when the two charges are very, very close to each other until the two charges go like the distance is like almost infinite. But it just, of course, when the charges move away, as you will see later, it goes so fast down, the electric force, so practically you don't see it. Okay. Now, when in the vicinity, you keep your original positive charge here, but in its vicinity, you bring another positive charge. So what happens to it? The two charges feel like a force is pushing them away. And if they were free to move, that's what would happen, all right? Obviously. Okay. Now, well, let me here, that's supposed to be E. So in this particular case, since we have electrostatic charges, so we are talking about an electrostatic force. And this force, if we were to ignore the direction that it will take, in this particular case, you see the direction of this force here, it would be like the way it shows. So it's going to pull one charge in and the other charge in. So next to the charges, they have that direction, all right? And which means that we know what direction is. And then in that particular case, we're looking at the value, how the magnitude of the force. And if you were to do that and look at the force as a scalar, because you know what the direction is going to be, then this is the scalar form of the force. However, we know that we cannot do that if we have multiple charges. So for example, in this case, let's assume that you have, right here for a second. Let's assume that you have 3 charges, all right? So one here and another here. So this is, say, Q2. The first one was Q1. And then another here, which is Q3. all right? And we want to find, now, of course, as you know, because there are 3 in there, there will be multiple forces, all right? So between Q1 and Q3 is gonna be, say, this one. Let me do it with green. And it's gonna push these 2 away, like this, okay? With between Q3 and Q2, it's gonna be, say, this one. And it's gonna pull these 2 close to each other, like this. And between Q1 and Q2, there is then this force, and it's gonna try to pull these 2 together. So what happens if, what in the question could be, what is the total force that each one of these charges feel? In that case, obviously you have the forces, but in different directions, which means that if you were to really find how much the total is, you have to take those directions into consideration. And you cannot just write down the forces as scalars. All right, you have to write down the forces as vectors. So for example, there is a force in Q1, how I would write them. So Q1 has 2 forces, 2 forces applied to it. So F, 3 on 1, and then is F from 2 on 1, okay? And then what the Q3 has? Q3 has F 3 on 1 from 1 and F on 3 from 2. And then here it has F from, from 2 on 3, and then F2 from 3 on 2, and here F on 2 from 1. All right. But you still do not have the total force that is exerted on each charge. So practically, to be able to do that, you will have to go to vectors. All right, so having said that, looking at this, we understand then when we start writing forces down, we cannot use scalar entities, but we're using vector entities. And what will be the best way to represent a force? First of all, we know that the force is along the direction that connects the 2 charges, the line that connects the 2 charges, okay? So you have Q1 and Q2. For now, assume that Q3 is not there because superposition applies, all right? So the other thing, you remember superposition? Superposition applies on electric fields and on forces. So for example, if I have somebody pulling me away and then another person comes and helps this person pull me away, I will feel it 2 different forces and you will have to sum them up because, you know, I will have to move in the same direction. So when forces apply and they are along the same direction, they sum up easily. But when forces are in different directions, you have to use vector properties to be able to sum them up. Electric fields the same. And you have, as you will see later, when I feel an electric field along one direction and then a second electric field along the same direction, then I can sum them up to find the total. So remember that. However, when later we are gonna talk about power, so I have a source and generates 5 watts. And I have another source and generates 2 watts. All right, one source here, one source there. And I am here as an observer. How much power do I feel in my place? Yes, I can find how much power is gonna come to me from one source. I will find how much power is coming to me from another, as you will see, but I cannot sum them up. Do you know why I cannot sum up powers from circuit theory? Yes, because it's VI complex conjugate, or VI if it's in the time domain. It's the product of two linear components, voltage and current. The same thing, electric field is practically voltage, all right? It's related to voltage. Magnetic field is related to current. So if the power is the product of the two, you cannot sum them up. So remember that, because a lot of students make a mistake, all right? They sum up power. No, you can sum up electric fields, you can sum up magnetic fields, you can sum up the forces, but not their power. Okay, so now I describe this vector F sub E, electrostatic meaning, as 1/4 pi epsilon naught. Epsilon naught is what? Do you remember? The dielectric constant of free space. Assuming that we are in free space is epsilon naught. If, however, the charge is embedded within a material, how much this epsilon naught is going to be? It's going to become epsilon. Where epsilon, all right, so in a material, to write it here as a parenthesis, so you guys remember it. In a material which is characterized by epsilon and mu, you remember those epsilon and mu coefficients for a material? Do you remember how we call them? Epsilon is the dielectric permittivity and mu is permeability. Epsilon shows how much the space can hold charge, and mu, it shows how much this space can hold a magnetic field, all right? So because, for example, you know what happens with lightning in storms. Can you tell me a little more about this phenomenon? What happens when we have lightning? Why do we have that? It is related to electrostatic fields. But what happens? So you have a cloud that happens to have an overall charge, say that this is negative, and then, or positive charge, because we consider the Earth, even it can be the reverse, but say positive charge on the cloud, and then you have the Earth that is like a huge ocean of negative charge. That's how you consider the ground. Ground is considered to be an ocean of negative charge. You have as much as you cannot spend. So what happens? You have a very high positive charge in one place up, a very high negative charge underneath it. So there is this force, but then the electric field, of course, the force will bring the clouds down, but it does not happen because there are other phenomena around it that does not allow this to happen, all right? So what happens? Then there is a very strong electric field because as you will see later, because of the electrostatic force, there is a very strong electric field between the cloud and the ground. And then what do we have? Dielectric, air breakdown. So the material under this very strong electric field becomes ionized and then practically becomes like a conductor. So there are all of the negative charges from Earth, they go all up into the cloud and they neutralize them through this very weird, all right, conducting path. So what says that not all the materials can handle any value of the electric field you want. They will break down. They will become ionized and then they will become conductors. So the charges will start flowing. And then in fact, in circuits, if you put too much voltage on a circuit and that happens, then it's gonna break your dielectric. And it's gonna destroy your circuit like you have put it in fire, something like that. All right, so that happens. And which parameter is responsible of this material? For that is epsilon. All right, so if we go here, I would say something important that F sub B, if you are in a material that has epsilon and mu, is going to be equal to 4 pi epsilon Q1, Q2 R squared A sub R. All right, where epsilon now is going to be the relative dielectric constant times epsilon naught for free space. Okay, so if you're in free space, it's epsilon naught. And this is always a constant that we know how much it is. Okay, one other thing I want to ask you, because you need to remember it. Being engineers, and we are going to see that later, but since now I remember that, because that's another mistake that I've seen. We are engineers. What does that mean? That we have to always calculate values and units. Values and units. If you don't calculate units, the value has no meaning. All right? Because, for example, if you don't have usually the electric field, what are the values, the units of the electric field? Volts per meter. We are going to see that. Volts per meter. All right? We're going to repeat it again. Okay. If you find, for example, you solve a problem, you find the force, and then from there, you find the electric field by dividing, all right, the force. So the electric field, electrostatic field that is created by charge Q1 here is practically the electrostatic force divided by the other charge Q2. All right, you remember that. That's how we define the electrostatic field. Okay, these are the fundamental things that you have seen in physics before. Now, if I give you everything in here, which you're going to have some problems like that, all right? I will give you Q1 practically for epsilon, for E, rather, electric field, not epsilon, E. I will give you Q1. I will give you the distance from the source. All right, I call them that source. My Q1 is here. I have removed Q2 because I took the force and I divided by Q2. So practically, I got now a quantity, which I call the electric field, E, which in fact only depends on the charge that produces it, and which varies with the distance from the charge as 1 over R, magnitude of R, because R is a vector also, all right, has different directions, R squared, which means that if I draw, my charge is all concentrated at one point, and if I draw a circle around this charge, then at every point on this circle, the electric field is going to have the same value, but not the same direction. All right, so at this point here, it's going to be like that. At this point here, and let me call this E, A, that's point A. At this point B, is going to be like this. This is B, and I call that EB, and so on and so forth, all right? Each of these points is going to have a different one. But what is it different among these all fields? Only the direction. The magnitude is the same because they are all at the same distance from the source, all right? So you can say that if my charge is a three-dimensional charge as it is here, it's just one charge at one point, then the surface on which the electric field has the same value, it's a spherical surface, spherical. Why is this important? Because if I can take this conclusion and I can apply to practical problems. So for example, if I have a small antenna that may look like, a very small antenna can look like a charge, even if it's not a static radiator, right? Radiators are not static, obviously, but the far field, as we call it, of this antenna is going to look like this. It's unidirectional and has the same value on spherical surfaces, which are concentric. And at the center of these surfaces is the charge. All right, so this is the information. And now this is important because from a very, very simple formula, you get some ideas about a very practical antenna. All right, so from here, what I would like to do then, after I wanted to remind you of those two things because this is not new information, but I wanted to use this as an explanation of why we have to go to vectors. You need to remember that the most important thing here is to understand the physics behind all of these things we are going to learn, but math is the language we are using. All right, so we all understand because it's the most elegant language that you don't have to write 2 pages to explain. Like I do now when I don't show you. I do explanations, take a long time, but when you write the formula down like this one, it says it all right, obviously. Okay, so now from here, we are gonna go and explain why we, just very briefly, all of these all of those is a review. Now, when it comes to vectors, all right, they belong to another family of functions. And in that family of functions, so this is vocabulary now, so you remember, there we have scalar functions that do not have direction. Could you tell me a scalar function? Speed has direction. Something is moving. Temperature is scalar. All right. Our weight is a scalar function, even if it's gravity due to gravity. But the way we say, we all understand that this one is the force that pushes us down, but it is a scalar function. Our height is a scalar function. All right. So all of those, they need only a number to say how much they are without direction. From there, we go to vectors. Vectors have a particular direction. So with the number, with the magnitude, you have to also assign to it a direction. And now when you say direction, that's where the next thing comes, which are the coordinate systems. Because it's okay to say, yes. Could you speak out louder? Which B? Oh, speed, because you go into a particular direction. It depends on how you use it, all right? You don't mean velocity. Yes, okay. All right. Okay, we're all together now. Yeah, if it is that, it's like the weight, all right, practically. Yes, speed, yes, can be a scalar, velocity, not. All right, good. Okay. So then so for example, I can say, well, this is the direction of the electric field, all right? So how are you going to characterize it mathematically on paper? I'm not gonna say that I have a point here and then there's another point, it's a little farther away, you know, to the left, to the right. No. So we are gonna use vector identities, all right, to not only introduce vectors, but introduce them in particular coordinate systems. And of course, vectors, we are going to work in 3 dimensions, even if we can always, for simplification of problems, you can always collapse the dimensions from 3 to 2, from 2 to 1, depending on the type of problem you're solving. But in general, we're going to have 3 dimensions, and therefore we're going to have either the Cartesian coordinate system or the cylindrical coordinate system or the spherical coordinate system. And then which of all of these we're going to take depends on the problem we're going to solve. All right. So we'll have with vectors talk about coordinate systems. And then there's a matrix. what is the matrix? Not the movie. The matrix is an entity that is characterized by multiple independent variables or like numbers, all right? It could be variables. There are many. You can have a matrix. Well, for example, a vector is a simplification of a matrix because if, for example, a vector has 3 coordinates, x, y, and z, then the values of these 3 coordinates can make a vector, right? So we call it vector matrix. When you say I'm multiplying a matrix by a vector, that vector and this vector we have here, they're not different. We may represent them in different ways. Okay, so a matrix is like you have multiple variables that characterize that entity. And then we have tensors, and tensors, so let me in fact also show you scalar quantities here, vector quantities are here. Okay, you will see them in my notes, all right? Matrices are like that. I have an example here where a matrix can be used, and we use it all the time. So for example, let me tell you this. It's very common practice right now when you have a large building like this to try to spend some time and try to regulate the temperature in every room, which in reality is a very difficult optimization problem. Why? Because the temperature variation depends on the size of the room, depends on whether you're on the upper floor, lower floor, if you have open spaces that the air is moving and the whole bit. And if you try to analyze that, theoretically, you can never get done, especially with complex buildings like this. A lot of times what people do, of course, there is a design ahead of time, all right? But those designs are not accurate. So the first time you occupy a building, nothing works in terms of temperature. Some rooms are totally cold, some other rooms you cannot be there because they are totally hot. So what people do, they play with the thermostats. They go and do a number of experiments. They put different, say if you have like 3 thermostats, you do 6 different possible combinations, all right? So you put a range of values and then you develop different combinations. And then as you do the thermostats, you go and measure every room, all right? The temperature. Now, by doing that, you create a matrix, which we will call it a transfer matrix, all right? It's like you have a system and then you create that matrix with a little bit of calculations, which then I can always use if I turn my thermostat 1 to this value and thermostat 2 to this value, then I can project what kind of temperatures every of the 4 rooms is going to have in this particular case. So in this case, I need a matrix to be able to characterize this problem, all right? When, however, instead of scalar functions here, as it is temperature, you have in their place vectors, but with the same kind of thinking, all right? Then you have to introduce a tensor. So a tensor, either you're gonna see it as a matrix where every element is a vector, or you're gonna see it as a vector where every component is another vector, all right? We're not gonna use tensors, but when you read, for example, about topics and then somebody talks about the tensor, you just need to know that is a way of characterizing different physical phenomena, all right? Where there is complexity in the physics involved. Okay, so with that, any questions before I proceed with vectors? Because that is the fundamental thing that we want to do first of all. So, okay, go to vectors. When we start talking about vectors, there are a number of things, okay, this is a review. There are a number of things that we will have to remember. That vectors, other than defining them in one of the coordinate systems, there are quantities that have very specific properties. And those properties are extremely important to remember. Now, you can prove those properties. I'm not going to ask you to do that, but I will ask you to remember the properties. And if you don't remember them by heart, I don't expect you to remember things by heart, but I expect you to know where to find something if you need it. There are some specific things that are so important and so fundamental that you will have to remember by heart, but there are some other properties that are more extensive. And if you need to use them, then you should know where to find them. All right, that's how we do things. Okay, in this particular case, what you see is that we have two vectors. And I have done the following. This is, in fact, this is just to give you a flavor and to just bring some things that you have seen before, but in reality, we're still in the review process. All right, now we look at vectors because we know that we need to use them to talk about the electrostatic fields and forces. But when we do that, and we're going to solve problems, of course, after probably by Friday, we're going to solve problems by using that to practice a little bit. So here you have two vectors. And each point A, so every vector is between the center of a coordinate system, X, Y, Z, and one is between O and A, so vector OA. The other is between point O and B, vector OB, and then we have vector AB. See, each one of these vectors has a starting point and ending point, has a direction, all right? It's not just the line along which the vector is, but also which direction along this line it goes. All right, that is important. So a vector can be written, now, one more other thing. Whenever you see A sub X with a hat, that means unit vector along the X direction. All the unit vectors will be the alpha or A, and it's going to have a hat over it. And A sub X or alpha sub X with a hat means it's a unit vector along the X axis. All right. So alpha sub Y with a hat is the unit vector along the Y, and the same thing with alpha sub Z with a hat. Okay. So for example, here, how would I write vector OA? If I wanted to write, which I have not done here, then vector OA would be X sub A times that unit vector plus Y sub A times this Y sub A sub Y plus Z sub A sub Z. All right, and the same thing applies to OB. All right, so from here, you can see that it's easy to get the difference between these two or the sum. All right, the sum of course, here the way I have done A, B is the difference between OB and OA. All right, but let's assume that I did not have the visuals and I wanted you to write OB plus OA, the vector. So let's assume that I had asked you to do this. Forget about the graphs. Or this, all right? So obviously, you know how to do that. You put one next to the other. You in the first case, you sum their X, Y, and Z coordinates, all right, respectively. And then in the other case, you subtract them. Now, it's good to know how to do this, but also it's good to be able to have the visual capability to see where the sum is, because a lot of times in classes where we have vectors in engineering, visualizing what you have is an important thing. All right, you remember from geometry. That's why we do geometry. You know why we do geometry? in high school, for those of you who do it, or in college, even if a lot of times you say, oh my God, you know, whenever in my whole life I'm gonna see this. Maybe never, but it helps you at that point to allow your brain to think in 3D, to visualize in 3D is extremely important. Engineers do have to visualize things, all right? You have to visualize the things that you're making. And so having that capability is extremely important to visualize where is A plus B, all right? To visualize where is A minus B. So that is important to do. The other thing that is also important is to remember, and the dot and the cross product. Okay. Now, all of these products, a dot A and B, why do we use that? If I see, let me ask you this question. When does A dot B go to 0? When does it go to 0? Yes. So, and of course the formula says it, but we need to understand that the dot product between vectors shows the correlation between the vectors. The vectors are not correlated if one dot the other is 0, all right? That's what we also say. So if two fields are perpendicular like that, then the inner product is 0. And when you see that coming out from any calculations, then you envision the two vectors to be at 90 degrees. If the dot product of two vectors is equal to the product of their magnitude, what does that mean? They are collinear, they are parallel, or they are along the same line, all right? So when you multiply them, all right, so it's exactly the dot product of the vector is the product of the magnitudes. Now, what do you also see that the dot product is what? Is it a vector? Is it a scalar? Is it a tensor? What is it? Scalar. So when you take the dot product, you only try to visualize how exactly, I mean, it's a measure of the direction of the distance of the angular distance between the two vectors. That's what it is, all right? So a dot product, it gives you that sense. And it's very important to have that capability to see it when you solve a problem, all right? So not to think it all mathematically, try to visualize it. Okay, cross product. The cross product is what kind of entity? Is it a scalar? It's a vector. Why is it a vector? It's very interesting. You can say, well, look, I have the difference between the cross product and the dot product is in one, I have a cosine, the dot, I have a cosine of the angle between the two, and the other have a sine, okay? But beyond that, the second has a direction too. And the direction of a second is perpendicular to the plane that is defined by the two vectors. All right, that is important too. So it says, as a matter of fact, that when the two vectors are perpendicular, that's when the cross product has the maximum value. All right, is sine of 90 degrees, 1. So when you see something like that, when you see A cross B to be 0, that means that they are probably collinear, all right? So it gives you a sense of what happens. So it's math, but in reality it tells you what happens in real, in the physics context. So that is important to remember. There are other properties. I wanted to speak about the unit vector here too. This is important because I talked about the unit vector. When you put a unit vector, it's okay we know how to use it, but in reality, how do you calculate it? Right? How do you calculate a unit vector? If it's, unit, it says one value. If it's along the x direction, we know where it is, one value. But that is only a direction, does not have any value in magnitude. But if you have a line, let's assume that I am in the coordinate system, in the Cartesian, and now I have a new vector, okay, here. And I know, somebody tells me that this vector has a distance d, I mean magnitude, which is maybe 3 centimeters. Okay, they gave it to me. But now I need to find the direction of the vector. And let's assume that I know where it's this. All right, so I can find all these 3 points. That tells you how to find the unit vector along here, because the unit vector along that direction is not going to be similar to the unit vector of the x coordinate or the unit vector of the y. It's going to have one as magnitude, but the direction is going to be different. And what if you have to express that unit vector in the x, y, and z? All right, a lot of times we may have to do that. So this is the formula that helps you identify the direction, all right, of a unit vector. You know the direction of A here. And then from that, you just take this, you divide it by its magnitude, and whatever comes out to be, that's your unit vector expressed in the x, y, and z coordinate system, all right? So with that, I'm going to stop. Today, I will give you a new problem, an exercise, okay, which is going to be here. And it's going to be based on properties. Oops. Okay, just a second. Did not recognize me. Where is the thing? Okay. Anyway, I will take my time because there is another class. You're going to solve this exercise by Wednesday before the class. Okay. All right. You're going to find an exercise which is going to be on vector properties, and then you will have until the beginning of the class on Wednesday.
In the first thing of notes, you use M to define magnitude. What would be the magnetic force then?
Yeah, what did I say? Let me see.
It was like page 2 of the first notes we went over. Yeah. I think it was down a bit more.
Yeah. This one.
So then, yeah, you said FM.
So no, I will, that means that F, thank you, FE.
Earlier you then put magnitude, so I thought you were just meaning.
No, it's supposed to be here.
Got it, thank you.
Yeah, you're welcome. I will put the new one up.
Sorry to bother you.
No problem.
So I was wondering, I was looking at my top hat from this weekend, and I was like, oh, sorry. I don't know why it's not letting me submit.
Then
And
where is the submit?
Also, I realized that a little bit later when I talked to my friend today that I was in 2021 and not 2022. So I submitted this one, but I know it was due before class, and I know there's no late work accepted.
You can do it now. I have not.
Oh, I've submitted it already.
Oh, okay, good.
Just I know that we.
But not the 21.
No, I resubmitted in the 2022 one.
Yes,
now. Will I still get credit for that one?
Oh yeah, until when I turn it off, you cannot submit.
Okay, okay. Thank you very much.
Sure.
So yeah, I've already talked to you, but yeah, I was originally in the 8 a.m. section, and I'm still in a group at 8 a.m. and I don't know if that's going to cause any issues.
You have changed your.
My section, yeah.
You have changed your section.
Yes,
Well, could you give me? Could you? Let me see. Could you give me your name?
Yes, ma'am.
Write it down if you can.
Yeah.
Or let me see. Yeah, probably. Yeah.
So I do need to be in a group in this section. So I did reach out to them on Canvas while I was working on the group assignment, but I never got a response, so I just did it myself. That's cool.
So let me see here. Why do you not guys?
Sorry about this.
Here, you were, I have all the names. What is you were in 501?
I was in 501.
What's your name on 501? Oh, okay. So now you have moved to 502. Okay, we'll see what I can do.
Awesome.
All right.
I have one more question. Oh yeah, so for exams, it is that exact same group, right?
Oh yeah.
The group that we're assigned.
Yeah, yeah. Those groups, now you're gonna be in a new one, but those groups do not change.
And then we through Canvas to get everything done.
Usually, I mean, the best way possible to communicate. Get into,
some of the other classmates. I think someone got the grade back, but then someone else didn't get the grade.
okay. Let me see Top Hat. Texas A&M. What is that? 1 second. Okay, here I am. Let me see. I'm on 502. What is your name again?
Marcos?
Yeah. Okay. Let me see. Grade book. Marcos Perez. Oh, you have a grade here. You got 60 out of 60.
Okay, got it.
Why do you not see
I
that?
don't know. Yeah, like on my grade book, it just doesn't show anything. It says
Maybe it's only there's a grade book, and maybe look at, are there any other other than grade book? What else do you have?
I just have classroom assigned, so like unanswered homework review. So like if I click on the quiz too, it doesn't show anything.
So that's interesting. I would need to, you know what I would suggest? Call them to see what happened.
Yeah, and I'll just
because you have a
make sure.
grade here.
Okay, got it. if anything, I'll just go ahead and call it later.
Yeah,
see if
call
it's not
them.
syncing or,
Usually they're very good. Yeah, they're very good in responding.
Okay.
So,
Okay, got it. Thank you.
all right,
Professor.
thank you.
Compliment.
All right.
You have a good